Okay. Any questions about? Are you ready for your exam Monday? Yeah.
On practice test, part C, if you have put measure variable, the manipulated variable, and the disturbance. And I wasn't sure about the disturbance.
I don't even remember what the question is. Let me see if I can.
It's an endless flow.
Measured variable and calculated variable and disturbance. Okay. So, what is the measured variable? There's a level transmitter, so that measures the height.
Right? So it measures the height and not the level. Is the height equal to the level?
Yeah, the level.
Okay.
The level measures the height of the thing. That's a measured variable. The manipulated variable is what the controller will manipulate, right? So that will be the valve that manipulates the flow rate. That's a manipulated variable. And the set point is that you set for a level controller. Now, is there a disturbance variable that you could R1 and R2 could be a disturbance? That is something that is not directly controlled by a controller, but you could upset the process by opening, for example, even Q2 could be considered as a disturbance variable. If you could just open up the tap, right? And
Not thinking of the manual valve. I was just thinking that for did it like saying.
yeah, this is where you can be very creative, and you need to know more about it. You know, are these tanks open? If they are open, if there is rain, that could be a disturbance, right? And that collects the water if it is a water tank. So you need to know more about to identify all the disturbances. There could be many, many disturbances, but the idea here is just to see whether you can identify at least one or two as potential disturbance variables in the problem. Okay. Any other questions? So you know my style of exam from the first midterm exam, and you know the content. Okay? So you should be very familiar with given a process model, identifying whether it's linear or nonlinear. If it is nonlinear, finding the steady state, linearizing around the steady state, developing the transfer function, and then given the transfer function for several blocks, putting the blocks together and doing an effective transfer function perhaps, and then examining the dynamics of the process with and without control. Okay, and so all these concepts involved will be tested at the most involving math. It's no more sophisticated than the quadratic. Okay. Oh, I just didn't. Okay. So in the last lecture, almost a week ago, we looked at this idea of developing an effective transfer function for a block, and we looked at a parallel system, a system with a recycle, and then we started examining individually the P, PI, and PID controllers, and I want to resume at that point. So this is for a valve. So we looked at specifically valve as a final control element, and what kind of signal that goes into the valve and what kind of output that it produces, and a model. Okay, so here we are looking at a valve with a controller on the valve. So if P is the pressure signal that goes to the valve sent by the controller, it's going to receive the error signal, which is the difference between the set point and the actual measured variable for flow rate, as an example. Okay? So it's going to be centered around PS as the steady state, the current steady state, and a proportional and integral action in this case. Okay? So the proportional action is proportional to the error. Proportionality constant is a tunable constant for the P controller. And for the integral controller, it's integral of the error. And we saw in the last lecture how would the response be for a specified error input. Okay? And this is not practical because you will never have an error maintained at a constant level. What happens is when you make a step change, the error will undergo a step change from 0 to 1. But the controller will start responding, and the idea is that the error will go down to 0. But what this tells you is how does the response signal change to the error signal. So if the error signal were a step change, all we need to do is to plot the graph that you see here in the top, given the bottom error signal. You need to know this equation, the equation that you have here, plug into that equation the step change, and that is P. Then plot P as a function of time. Okay. So if you take this, then you will find P as a function of time as equal to Kc times a step change. So that's just 1. Okay. This is for t greater than 0. Okay. Plus Kc divided by tau I times integral of 1 times dt, 0 to t, plus Cs. So that will give you PS plus Kc divided by tau I times t. Integral of 1 dt is t. Okay? And that's what this upper graph is. PS, initially it was at PS. At time t equal to 0, we put a step change in the error. So that immediately gives you a Kc, so plus Kc instantaneously. And then there is a linear variation with time. That part is the part due to the integral action. So that is the main thing that we get. The integral action, if there is a constant error, the integral action becomes more stronger and stronger and stronger with time. The idea is to get the error down. Okay? So when that happens, the error will spontaneously go down. That is the dynamic interaction. Here we are saying there is no interaction. I'm just putting a constant error. This is how the controller will respond. The controller should respond. Okay, and there are 2 parameters in there that we need to tune to adjust the dynamics of the response. Okay, and we are going to do the same thing for the other controllers. So if I have, well, the transfer function for a proportional integral controller, simply taking that equation that we had before and doing a Laplace transform. So this is the transfer function, which relates the input, which is the error to the controller, and the output to the final control element, which is the pressure signal going to the valve. Okay, and the proportional derivative controller. Again, we saw this very quickly in the early part of the course. Is one that says that this is the steady state. I add a proportional part, one that is proportional to the error, the other one that is proportional to the derivative of the error. So the idea here is it anticipates the error change, so it can make the response much more quicker because it knows how fast the error is changing. Okay, so based on that, the control action is adjusted. The integral action looks at how much of error is accumulating over a period of time, and if that accumulation keeps on increasing, it will increase the action to decrease the error. Whereas the derivative action looks at instantaneously how fast the error is growing. The error is growing very fast, which is measured by d epsilon dt. Then I need a stronger action to decrease the error back to 0. Okay, so that is the model for a PD controller, proportional derivative controller. And how does the response look like? We can do the same thing. In this case, what we are going to do is we're going to say that the error I'm going to maintain increases linearly. Okay? Remember, the derivative controller looks at the rate of change of error, and if the error is constant, the derivative action is 0. Okay? So it doesn't give us any information if the error is constant. So only when the error is increasing, it says how fast is it increasing so that I can adjust my control action. So if the error is increasing linearly, A times t, then you take that and plug it into here, and you're going to get PS, which is the steady state part, plus the proportional part, which is A times Kc times t. What I've done is I've substituted for epsilon here, A times t. So I get Kc is already there, so I get A Kc t. Then I do the same thing for the derivative part. When you take the derivative of d epsilon dt, I simply get A, and then I already have Kc times tau d. Okay? So this is how the response of the controller will be for a PD controller, and we can sketch that. So the sketch is given here. So the lower part is the error. So the error is 0 initially, and at time t equal to 0, the error increases linearly. How does the response of the PD controller look like? It immediately, the proportional part immediately increases it by this amount, and if you had only proportional part, the response will be a constant one. Okay? But you have the derivative, in this case the derivative alone, that's the one that gives you the increase. Let's go back to the equation. Okay? So the proportional one gives you a linear increase with time. It is the derivative one, because all these are constants. It gives you a step change in the response of the controller. So this part is entirely due to the proportional action alone. Okay? And the derivative action is, I did it again. I think you might have stuck with that. Okay? So this constant part is coming from the derivative alone, and the proportional part is this part, because it is increasing with time. Okay? The error is increasing with time, so the response is increasing with time, and this is the combined one. Combined P and the proportional and the derivative action. Again, these are just to break up and understand individually how does the controller respond when you have various types of errors. But none of them would be exercised in reality, because in reality the system will respond to the control action and the error will be driven down to 0. Any questions on that? Yeah. Okay. So the PID controller basically has an equation that looks like this. That is the steady state part plus the proportional, the integral, and the derivative part. So that would be the ideal controller, because it gives you the ability to handle all cases. Okay, the case where you just want the error, the response to be proportional to the error, and it will, if you have only that, it will give you an offset. So you add an integral action which reduces the offset, because it accumulates the error and increases the control action based on the accumulation. And the derivative action will give you a quicker response, because it looks at how fast the error is moving and generates a response action based on that. And its transfer function is given by simply taking the Laplace transform of that, and there are 3 parameters that we need to tune. And we are seeing that Simulink gives us a built-in module for implementing that particular transfer function, which is a PID controller. Okay. So we also saw this one, but I want to build on this idea of how do we develop an effective transfer function. We saw this in the last class without a disturbance. Now I'm going to do both examples, with and without disturbance. So the first question is, given a block diagram like this, we know how to get the transfer function for the process from the process dynamic model, or we will see later on in the course how to get it from an experimental data. That's the transfer function that we need to describe the dynamics of the process. We know how to get the transfer function for the measurement. Okay, and this is the final control element, valve typically, okay, or a heating element, and this is the controller. So we have studied in detail all of them, and now we are synthesizing, we are integrating all of them. Okay? So this is the set point, and this is the process variable that we wanted to control. So we are measuring it, and we want to control it. So we saw in the last class how to obtain C divided by R or R divided by C. Okay? So I'm just describing in detail what the various elements are, and the problem is find out C over R, the output over the set point. And the simple rule that comes out of this is what I want to illustrate today. Okay? We know how to do it algebraically. Algebraically, how do you do? Simply take each block, relate the input and the output, write down a set of equations, and eliminate all the intermediate variables. Keep only the variables that you need, C divided by R. If you understand that, you can apply the same process to relate U divided by R, for example, or U divided by C, whatever the combination is in that diagram. The process of elimination to get rid of all the variables and keep two variables. Okay? So we will do both of them. Okay? C divided by R and C divided by U. Okay, so this diagram shows you how we can collapse. In the first case, U is 0. There is no disturbance, and there is only a set point, and this is the process variable. Okay, so since there is no U, we have removed this part, and all I have is GC, G1, G2. So the effective transfer function for that are in series is simply G. So G is going to be the product of GC, G1, G2. Okay, so we're replacing all the three blocks by a single block, G. Okay, and then we have the feedback, which is the measurement block H. Now, if you want to relate simply R and C, you can replace this by an effective transfer function. This is not parallel. Parallel would mean that the signal is going in the same way from input to output. This is the feedback. Common mistake that you can make in an exam. Okay, just because two blocks are next to each other, it doesn't make it parallel. It's a connectivity that tells you whether it's parallel or feedback. In this case, the signal is going this way. Okay, and this is a feedback. And you also have to notice that the plus minus sign will have an influence on the plus or minus here. So if it is a plus minus, it's a negative feedback, and then the formula is simply G divided by 1 plus GH. And the way to remember that is between the output and the input, take all the transfer functions that are in the forward path. Okay, that goes into the numerator. That is G. And take the complete transfer function in the entire loop. Okay, in this case it is G and H, so G times H. And you always add 1 plus if it is a feedback, or 1 minus if it is a positive feedback. Negative feedback versus positive feedback. And you can show this by simple algebraic manipulation. Okay, any questions on that? That simple rule, if you remember it, it will make your analysis in an exam very easy. You don't have to go through the algebraic manipulation every time. If I particularly give you a complex block diagram, you can reduce individually in sections and then collapse it into an effective one. We'll do a few examples of those. The denominator is always 1 plus GH, 1 plus the entire block in the loop. So in this case, the loop contains two transfer functions, G and H. So it is the product of G and H. Whereas in the numerator, it's only the open loop, the forward one. So cut off the feedback. Okay, so yeah. No, if it is a negative feedback, this will be plus. If it is a positive feedback, this will be negative. 1 minus GH. Okay? Did you have a question? Okay. Yeah. And if you don't remember that, if you're in doubt, always follow this algebraic procedure. The algebraic procedure simply says that C, the output is, in the open loop case, GC, G1, G2 times epsilon. Epsilon is the error that comes in here. So all I'm relating is C to epsilon. So that is simply the product of GC, G1, G2 times epsilon. Okay, and then I'm saying I'm going to let G be the product of these three. So what I have is the C, the outlet, is equal to G times epsilon. But epsilon is R minus B, negative feedback. Okay, so I can substitute that epsilon into that equation, and B is related to H times C. This is C. B is H times C. These are the algebraic equations relating the input-output of every element in that block. Okay, and it's just a matter of combining. So I take epsilon, substitute in there, and what I get is C as equal to G times R minus B, because epsilon is R minus B. Okay, and that is the same as G times R minus B. B is H times C. Okay, I'm eliminating all those variables, so this I get as GR minus GH times C. And then take this to the left-hand side and combine as C times 1 plus GH equals GR. So C divided by R is equal to G divided by 1 plus GH. Okay? So the algebraic process is the one that leads you to this rule, but the rule is easy to remember. All the block diagrams in the forward open loop divided by 1 plus everything in the loop. Okay, any questions on that? Now remember, we are focusing on how to do the effective transfer function, but each one of those GC, G1, we already know how to get it. Okay, so we still need to put it into this and look at the output to step change response, the stability, and all those things. So the next question is, what is the relation for a load change U? Okay, so can you simply, I guess I've given you the answer there, you should have hidden it. Apply that rule and see whether it is consistent. Okay, so if I want the relationship between C and U, the output to the input, now I'm going to set R equal to 0. There is no set point change, so only measurement noise, and I want to see how does the system respond due to the measurement noise in the presence of this controller action. Okay, what would be the purpose of a controller in that situation? The set point is 0, but there is measurement noise coming from there. Some noise coming into the process. What would be the objective of the controller? Disturbance rejection. So it wants to get rid of whatever the disturbance is coming through you. It wants to take appropriate control action such that the disturbance is gotten rid of. Okay, that will be the goal. Okay, so what would be the effective transfer function that relates the output from the process versus the disturbance that is entering the process? Is it going to be simply G2 times U? U certainly affects this way, and R is 0, right? So will, for example, GC, G1, and H affect C? It should affect C. Why should it affect C? Because you are measuring C and sending that to the measurement variable, and even though the set point is 0, this signal goes to produce an error signal, and the controller action generates an action, and the control valve implements it. Okay, so there is a signal that is flowing through this and back into the process, superimposed on whatever U is coming. The idea is that the effect of U should be annulled, it should be cancelled. Okay, but if you apply the same rule, the thing to recognize is that there is a feedback, but there is only the feedback forward path that we need to look at in the numerator. So between U and C, it is only G2. So GC and G1 doesn't have any influence on the numerator. In the numerator it's only G2, but in the denominator it is 1 plus, and that again is plus because it is a negative feedback. 1 plus the entire product, which involves G2, GH, GC, G1. Okay, that is the rule. The rule is whatever is between the 2 points, input-output points, whatever block that appears in the numerator and the feedback, it's that 1 plus all the blocks. Okay, any questions on that? Now, you should be, in an exam I might say show this, which means you should be able to write down the equation and develop that relationship algebraically. Okay, or in a problem I might just say here is a complex network, just develop the effective transfer function. So you can use this rule to simplify it. Okay, here I'm just showing the algebraic manipulation for this particular part. Okay, so I will let you kind of look at that. But this rule, well, if you cannot remember this rule, I can put it in a formula sheet. Okay, y versus x, output to input, is product of all the transfer function in the forward path divided by 1 plus all the transfer functions in the loop, in the entire loop. Okay, here is a more complicated example. Okay. So I think the question asks, find C over R, first part, C over R, okay, and the second part is C over U1, C over U1, and the third part is B over U2. Okay, would you like to try now? And also find the relation for C in terms of both R and U1. What does that mean? The output C when I change both R and U1. What kind of idea you would use to develop that? You would add the two transfer functions, but you said something before, parallel. It's not. It has nothing to do with. It's superposition. Two signals coming into the problem, and the effective response. Because each one of these blocks is linear, you can add up the response of individual excitations coming from either R or U1 or U2. Okay, so you can just add them up. So it's not a parallel structure, but it's signals are coming parallel. At the same time, meaning at the same time, and you can add them up using the idea of superposition because all the blocks are linear. Okay. C over R, I just used the rule. I didn't really algebraically show it, I just used the rule. What is the rule? The rule is in the numerator you will have the product of all the one in the open loop. Okay, that is GC, G1, G2, G3. GC, G1, G2, G3. That is what is between C and R. Okay, if you open the loop, that is if you cut this part off, then the output C is affected by R through these four transfer functions in series. Okay. Now if you have two in parallel, you would have to first collapse the two in parallel into an effective transfer function. Okay. So as the when I am relating C to R, I'm saying that there is no other excitation. So U1 and U2 are 0. Okay. But the second part of the question says when both R and U1 are present, find out what C is. So there are actually four questions here. First is find C over R, C over U1, B over U2. So in each one of those cases, you are assuming either R or U1 or U2 are present alone. Nothing else is exciting the system. Okay? These are the three inputs into the process, but only one of them is active, the other two are 0. Okay? And then to get an idea of what happens when both are present, it's a superposition principle. So you just add them up. Okay? And that's what the next question is, C in terms of both R and U1. We will do that. So to just get C versus R, it is the entire product of all the transfer functions in the forward path, which is GC, G1, G2, G3, divided by, you look at this sign, this is a negative feedback, so it is 1 plus the entire product in the loop. Okay, so in addition to GC, G1, G2, G3, you also have H1 and H2. Okay, so that is your effective transfer function. This idea of breaking it down into individual transfer functions is very powerful because now with this kind of an ability to analyze more complicated network structure, we're simplifying our algebra. Okay, we're reducing it to simple rules, and so we can analyze much more complicated system very easily using the same tools in MATLAB. Any questions on this one? Okay, so the next one is C versus U1. Okay, so let's go back to this. C divided by U1. So what would that be? C divided by U1. What are the transfer functions in the forward block between C and U1? G2 and G3. So it's going to be G2 and G3 divided by 1 plus y minus. If you have a doubt, just do the algebra. Okay? If you have a doubt, just do the algebra. The feedback here is coming here. Okay, the loop is going back from here, right? So this is a negative feedback. So here you are adding and subtracting. Okay? Whereas these are just disturbances. The disturbances are added. Both of them are added. But this is not part of a negative feedback. So the thing that one could get confused here is because I have both pluses here, how does that affect the transfer function? You need to do the algebra to see that it does not affect the sign at all. The sign here is determined by the feedback, the negative feedback, because here you have epsilon, and that epsilon is going to be equal to R minus whatever that comes here, that is B in this case.
Oh, okay.
Okay?
So is that sign on going up?
Yeah. If this were positive, then you will get a negative sign here.
Okay.
Okay? A negative sign in this place. Because in the denominator it is 1 plus the total, all the transfer functions in the loop, if it is a negative feedback. And we have shown that algebraically. But what I have not shown is what will it be if it is a positive feedback. Okay? Positive feedback is rarely used because it will always lead to unstable systems. Okay, so this, and now in the denominator you're going to have the product of everything. Everything meaning GC, G1, G2, G3, H1, H2. Oops. H1, H2, product of all of them. Okay, that is the effective transfer function if only U1 is non-zero, U2 is 0, R is 0. Okay, and I think that's what you will find here. Okay, so G is defined as the product of all of them in the loop, GC, G1, G2, G3, H1, H2. So the same rule now between B and U2. Now you need to worry about what is the forward path for B and U2. Okay, so let's go back to that figure. And what is the forward path between B and, what was it, U2? Yeah, B and U2. Okay. So you start at the input, in this case U2 is the input, and follow the path to the output, which is B in this case, and the signal is going this way. So it is G3, H1, H2. So that is a forward open loop product of all those. And in the denominator, it's the complete loop once again. Okay, so there is 1 plus G in the denominator. Is that clear, the rule? Okay. So as you're given more complicated ones, if you apply these rules systematically, you'll be able to get effective transfer function. The last question was the simultaneous set point change and the disturbance U1. Both are present. Okay, it's simply the addition. We already have the transfer function when only R is present, which is this part, and we have a transfer function when only U1 is present, which is this part. When both are present, it's the summation of those, and the principle that allows you to do that is the superposition linearity. Okay, and if all three are present, it's going to be a summation of all three. And at this stage, you should be able to analyze either using MATLAB or using Simulink for this complex response C to any disturbance and any set point change. Okay, and another example. Find the transfer function y divided by x for the following diagram. Do you think you can do that? What point am I trying to? Yeah. Exactly. That's all you need to do. So you need to look at this first and replace it by its effective transfer function. Okay. And then you have basically two transfer functions and with a negative feedback loop. But here you have a positive feedback loop. This is a feedback loop, but it's a positive feedback loop. Okay. So how would the effective transfer function for this one look like? Let's call this as G1 and let's call this as G2. So what would GE be for that inner loop that I've shown in green? So it's going to be equal to G1 divided by 1 minus G1. Okay? Because it is a positive feedback and there is no other transfer function in the loop. Okay? So you get the forward one in the numerator and you get the same one in the denominator too. Okay? And the next step would be G, let's call it big E, which is the ratio of y divided by x. So what would that be? GE times G2 divided by 1 minus GE times G2. 1 plus. Thank you. I think you're getting the idea now. So you can expect one question on this control block simplification, and so use the rule. Okay, I don't expect you to derive anything, but use the rule just to know that can be done. And then one more linearization and one on something else on control, actually getting the solution. So let's go back to this problem, and what we are going to do now is look at in detail dynamical response for P, PI, PID control for one of the problems that we have already seen. Okay, so proportional control for a servo problem. It is sometimes called a set point change, or basically you are tracking a change in the set point. So that's called a servo problem, and we're looking at only a proportional change. And the time constant for the measurement time is 0. Time constant 0, so the measurement transfer function is just 1. Okay, and we already saw that the heater, the gain is 1 over WC, and PR is the set point change. TI is the disturbance, inlet water temperature. So how does the response to proportional integral derivatives make the system change its response? Can we do that by MATLAB? Can we do that by simulating? So we're going to look at this problem for a variety of cases like this. Okay. So T prime divided by PR prime, the outlet temperature to a set point change. Okay, and that is going to be for that block given by GC times A divided by tau S plus 1. This is the effective transfer function. Okay, because in the forward block you have GC, G1, I guess, and 1 over WC. And this is the process transfer function, 1 over tau S plus 1. Okay. So using that idea of collapsing it, you're going to get an effective transfer function simply as Kc times A divided by tau S plus 1 plus Kca. Okay. Now, the reason that we do not leave it like this, but write it like 1 here, is what? Why do I rewrite it as by dividing everything by 1 plus Kca? You need to write this transfer function as something times S plus 1. Then only you can look up the inverse Laplace transform. The inverse Laplace transform of that is going to be always e to the power this something here times t. Okay, so this becomes the effective time constant. The process time constant is tau. Okay, so the interpretation is now, once you have this effective transfer function, tau 1 is your effective time constant when you have control. Okay, so what does it do? If Kc is large, you are dividing this by a larger number, so the time constant becomes smaller, the effective time constant. Okay, so you can speed up the response. Okay, that's what the purpose of a controller is. So it gives you a measure of controller. When you tune the controller value Kc, how does it affect the effective time constant for the whole process in the presence of a feedback controller? And what is A1 in a similar way? A1 is the effective gain. Okay, the gain, that is the ratio of the output to the input signal, T prime divided by Tr prime. That is the effective gain. Okay. And from the final value theorem, we know that the steady state value is given by A1 times Tr prime. How did I get that? For a step change, final value theorem simply says multiply by S and put S equal to 0. Okay, so when I have a step change, I will get Tr prime is all over S multiplied by S and then put S equal to 0, and you will get A1. Okay, so you can find out what is the ultimate gain in the presence of this controller, and that the controller gain has an influence on that. Kc is your controller gain that you tune as a controller engineer. So that's going to affect the effective gain for the whole process. Okay? And you can find out what the effective gain is and find out what the final steady state value is. And you can find out analytically what the offset is. Okay? So the offset is 1 divided by 1 plus Kca. So the offset is always going to be there when you have only proportional action. So analytically you can show that only for first order systems. And the only way to decrease the offset to 0, offset, remember, is the difference between the set point and the final steady state value. Okay? The only way you can do that is by making Kc infinitely large. If Kc goes to infinitely large, then you can reduce the offset to 0, but it will make the system unstable. Now, I need to relate this to stability. How do I relate the effective transfer function that I have to the stability? So if I have something like G1, G2 divided by 1 minus, say, G1, G2, or 1 plus, whatever. How do you determine the stability of such a system? We are now talking about stability not of the dynamical system, but the stability of the feedback control system, because this is the effective transfer function for the feedback loop. How do I determine the stability? That's a practical way of finding it. I don't think you would want to do that in a real plant. What happens if it's unstable? You make a step change and it blows up, right? So you want to do it analytically before you make a step change. You can do that. You can take this and do I Laplace, inverse it, and find in the time domain you will get e to the power lambda 1 t, e to the power lambda 2 t, whatever, and you can see whether lambda 1, lambda 2 are the real part of it is negative or not. Remember, really from this point onwards in this course, there's not going to be any new material. We've seen and assembled all the material that we need. Okay, we're going to be reapplying it in different contexts. So we are now looking at, once I have the feedback system in place, how do I get the effective transfer function? How do I get the response of the total system as I change my controller parameters, Kc, tau I, tau d. That's what we're going to spend the next few lectures on. And then we're going to look at stability. Okay? So at this stage, I'm asking you to see whether you can relate what we have seen before to what I'm presenting you here. So here is an effective transfer function. One way would be to put a step change, and in the simulation you can see whether it blows up or not. Another way is to do the I Laplace and get the result. These are a simpler way. Remember, we want to do simple. We don't want to do eigenvalues of what? Here I have an effective transfer function. It's a single input, single output system You're going to generalize this to multi-input, multi-output, then you'll get a matrix, then you'll get the eigenvalue of the matrix. Here, all I have is a single input and a single output, okay? And I have an effective transfer function that contains the action of the controller KC in it. So as I change KC, the dynamics can change, can become unstable. So how do I look at the stability? How do I get the stability? Well, I need to calculate the eigenvalues. The eigenvalue information is not in a matrix, it is in the effective transfer function. And I think you have it all over, but I want a specific answer. What is that specific answer? What do I want to do? Okay, at this stage I give you an effective transfer function in the following form. Okay, let me just open up. So the effective transfer function is 1 over tau 1s plus 1, 1 over tau 2s plus 1 divided by 1 plus 1 over tau 1s plus 1 multiplied by 1 over tau 2s plus 1 multiplied by 1 over tau m s plus 1. This is the effective transfer function, okay, between the output and an input. Okay, so obviously you can build a Simulink block. I should give you tau 1, tau 2, tau 3, okay, and there may be a K1, K2, K3 as well. You can build a Simulink and you can put a step change in C, okay, or you can use that. You can do the inverse Laplace transform. What do you need to do before you do the inverse Laplace transform? You need to do a partial. You need to write this in the form of partial fraction. So you need to factorize the denominator. Okay, and it is the characteristic roots of the denominator. The denominator is going to be a polynomial in S. Maybe a third order S cube, S squared, S plus 1. Then you will have 3 roots. Okay, each one of those roots will give you something like, if I write it in partial fraction, A divided by tau S plus 1, let me call it A, B divided by tau B S plus 1, plus C divided by tau C S plus 1. In order to go from here to here, you need to do the partial fractions, you need to simplify it. And because you're going to get effectively a third order system, you'll have 3 something like that. Okay? So it is the time constant of these that will determine whether the system is going to be stable or not, because each one will give you something like e to the power tau a t when you go to the time domain. Okay, so the characteristic roots of the denominator, which is written as 1 plus g equal to 0. So take the denominator of the effective transfer function and set that equal to 0 and solve for the roots. If it's a quadratic, you'll get 2 roots. If it's a cubic, you'll get 3 roots. Each one is an eigenvalue, okay, of a corresponding 3 by 3 system. And so you need to now look at the real part. Are they in the left half plane? That's what will tell you. And controller design, one aspect of controller design is to make sure that as you are changing KC, tau I and tau D, you always keep the 3 roots in the left half plane. So there is a method called the root locus method that we are going to see. Okay? The basic idea there is, as I change KC, how do these eigenvalues move? Is there a value of KC where the eigenvalue will cross to the right half plane, become positive? That way I can know whether it's stable or not. Okay? So really, all the ideas that we have seen, that we are going to be applying it in different ways. And one of the things at this stage that you need to be able to link is the stability of this combined feedback system is determined by the characteristic roots of the denominator of that effective transfer function. Am I making sense? Okay. Yeah, I guess maybe we'll stop there and continue on Wednesday with the lecture. Monday. If you need any formula included in the formula sheet, please let me know. I will use the same one in the first midterm and add anything else. So one of the things that I will add is this effective transfer function.